selectivity of boundaries of the same component of meromorphic.
Okay, I would like to thank the organizers for the invitation. And well, some of you may have already seen this talk. Nuria last year in Chęciny was talking about it, but well, this version has some advantages because we during this year we have corrected some of the errors, maybe not all, but anyway. Okay, so this is I will just describe our recent paper by our team with Nuria, Xavier, and Bogusia. This is our logo, by the way. Okay, so it is the paper on the local connectivity of for meromorphic maps. So local connectivity is a huge subject in holomorphic dynamics. So I will just say a few words as an introduction for non-specialists, but many of you for sure know this subject well. So maybe just the basic definition. A set is locally connected if for at every x we have a sequence of arbitrarily small connected neighborhoods of well, of this point. And why this notion is useful in holomorphic dynamics? Well, if we have, say, invariant Fatou component U of a holomorphic map, then suppose it is simply connected. So we have Riemann map from the unit disk. Here we have a map F, and here we have corresponding mapping G on the unit disk. And well, if the boundary of U is locally connected, then the Riemann map can be extended continuously to the boundary, and usually we can extend the conjugacy also to this boundary, which give us much information on the map on the boundary, giving some nice description. So that's the main motivation. Well, we have an initial remark that for the Julia sets to be locally connected, we must be connected. So a locally connected Julia set is always connected, because otherwise we have plenty of components, yeah. Small components. Okay, so we discuss two things: local connectivity of the boundaries of Fatou components and local connectivity of the whole Julia set. What is the relation between these two things? So first, Torhorst theorem says that if a continuum in the Riemann sphere is locally connected, then each component of the complement of this continuum has locally connected boundaries. So for Julia set, it means that if the Julia set is is locally connected, then all Fatou components have locally connected boundaries. On the other hand, there is something called Wyburn theorem or Wyburn criterion, which says that if all the boundaries of the Fatou components are locally connected, and for every epsilon, there are only a finite number of Fatou components with a spherical diameter greater than epsilon, then the whole Julia set is connected. And again, this is a topological theorem.
A question?
Yes.
Is there a counterexample when the second condition is omitted and the statement will be false?
Yes.
I don't know.
Yes.
Maybe
Isn't it an if and only if statement, this Weibull theorem? So I mean, it has nothing to do with Julia sets. It's
yes.
isn't it some if you have some compact set and
Yes, but
the boundary of the complementary component.
yes, I think you're right. It's just there's no. I think because
Yes, there is.
No, I
We
think
have a counterexample in our paper, Walter, I think.
so it's a I think it's an if just Weibull theorem.
Yeah, fine.
If and only if statement.
Yeah.
So and so from this you can construct counterexamples.
So, si no ho entès malament.
But I don't know.
We have an example. Deia el banc.
Okay, if of course, if you have a completely invariant component, Fatou component, then its boundary is equal to the whole Julia set, and then the local connectivity of the boundary is exactly a local connectivity of the Julias. And the basic example here is the basin of infinity for polynomials. So historically, many people studied this problem of local connectivity starting for polynomials. So it's from the 80s. There are works by Thurston, Sullivan, Dwade and Hubbard, Branner and Hubbard, then the famous technique of Yoko's puzzles, also Shishikura, McMullen, Lubitsch and Kahn, many people. So these papers were dealing with the local connectivity of the basin of infinity for polynomials, and it is noteworthy to remark that all bounded Fatou components for polynomial maps are always have always locally connected boundaries. In fact, Jordan curves, and this is the result of Pascal Roche and Yin. Of course, here there's an exception, a boundary of Siegel disk and images of Siegel disk can be non-local. What about rational maps? So from the 80s, it was known that hyperbolic rational maps have a locally connected Julia set, also sub-hyperbolic, which means that we allow some pre-periodic critical points in the Julia set, and the strongest result here is for geometrically finite maps. So here we allow also parabolic points. I will give precise definition later. And this is the paper by Tanley and Yin, and also Tanley and Peter Hayshins. And we know that for a wide class of Newton maps, the Julia sets are locally connected. So classical work by Pascal Roche, and also recent works by Konstantin Drach and Dirk Schleicher and Wang King and same. So this is a short survey of the results for polynomial and rational maps. What about transcendental maps? So for transcendental entire maps, the situation is quite different, because if the Fatou component is unbounded, then it cannot have locally connected boundary. In fact, sorry. If the Fatou component is unbounded, then the only situation it can have a local connected boundary, it is univalent Baker domain. So a Baker domain and the map is univalent. And moreover, the whole Julia set cannot be locally connected if there exists an unbounded Fatou component. So here one studies just bounded Fatou components, and here's the remark that a simply connected bounded Fatou component, if the boundary is locally connected, then in fact it is a Jordan curve. It is just by maximum principle because the map is entire. So here we know that for hyperbolic transcendental entire maps, bounded Fatou components have locally connected boundaries. In fact, the Jordan curves and in fact quasi-circles. This is the first paper was by Morosawa. If we additionally assume that there are no asymptotic values and there is some bound on the number of critical points in each Fatou component, then the whole Julia set is locally connected. So this was result also by Walter Bergweiler and Morosawa, and also with Nuria and Lassen. So I think the strongest result here is by Alhamed, Rempe, and Sixsmith about the transcendental analog of geometrically finite maps. So maybe I will give here a precise definition. So we have the set of singularities, the post-singular set. In meromorphic case, some terms can be not defined, so we neglect them. And in the paper of Helena Michalewicz-Brandt, and then in this paper by Alhamed, Lasse, and Dave Sixsmith, they extend this definition for transcendental maps. So we say that a map is geometrically finite if the intersection of singular set with the Fatou set is compact. So it does not approach the Julia set. And the closure of post-critical set in the Julia set is fine. And it more or less means that we have a finite number of attracting or parabolic bases. So there can be a finite number of pre-periodic critical set in the Julia set and also parabolic. Okay, and also in this paper, there is a notion of strongly geometrically finite map. So we add the assumption that in the Julia set, there are no asymptotic values. and the local degree at all points of the Julia set is bounded by a universal constant. Okay, and what are the results then? First, for strongly geometrically finite entire maps, we have locally connected boundaries for all bounded periodic components. Okay. Additionally, if we assume some bound on the number of critical points in each Fatou components, then this is true for all Fatou components. And if we assume even more a uniform bound on the number of critical points in each of the Fatou components, then we have local connectivity of the whole Julia set. So I think these are this is what we know about entire maps here. And note that all these results hold only for bounded Fatou components and for maps from class B, because all these class hyperbolic, subhyperbolic, and geometrically finite maps are in class B.
Excuse me, I have a question about the second part. Doesn't geometrically finite imply that you can have only finitely many critical points in the bounded Fatou components? So geometrically finite means that the set of singularities is compactly contained in the Fatou set, right?
This is a uniform bound.
Points over one critical value.
Yes.
Oh, yeah, I see.
So here we have a bit different situation than in rational. This critical points and critical values. Okay, so now about meromorphic maps. So we started to look what is the situation for the transcendental meromorphic maps. So here are two pictures. So there are two maps, in fact, two Newton's maps, Newton methods for entire maps. The first one is Newton method for z plus e to the z, and the second for 1 plus z e to the z. So you can see some, here there are some attracting basins, here there's some Baker domains. But you can see that on the right, you have some structure of hairs, like for exponential. Yeah, you can see these hairs, and apparently there's no local connectivity. If you have this comp-like structure, it prevents you from being locally connected. But on the left, the situation is different. There are no hairs. Well, these components are unbounded, but still they look very regular. So we thought that in this and similar situation, maybe there is a chance to prove local connectivity. And we introduced a class of tame Fatou components. for this aim. So what is a tame Fatou component? So this definition is well not complete, because it says that an invariant Fatou component is tame at infinity if all its unbounded parts are contained in something called repelling petals at infinity. But at the moment, I have not defined this petals at infinity, so you must wait. But these petals at infinity are something that should resemble repelling petals of parabolic fixed points. Okay, some regular movements from infinity to the bounded part, because it's repelling. And we assume that the map is univalent in each of this petal. Okay, so this is the definition, a finite number of such regions, and we also assume that one region is not mapped into the other, so they don't. Okay, to formulate the result, I need some notation. So here the post singular set is divided into post critical set and post asymptotic set. Again, this some of these terms can be not defined. Here we know the closure in C, not in the Riemann sphere. Okay, this is accumulation set and local degree of the map.
Set, we move by accumulation.
What does the right
Set. Yeah.
It's a combination.
Yeah,
Just not to use prime for the set. Okay. Okay. So this is the result. So we aim at proving this local connectivity for different types of Fatou components, but to start, we have done something for invariant basins. So we assume that we have an invariant basin, which is simply connected. And maybe I will explain it on the picture. This is U. It has some unbounded parts. The first condition here, what it means? It means that we have some compact set L, and here we can have plenty of post-singular set and total mess. Okay, but outside this compact set L, we can have only discrete set of post-critical points, no post-asymptotic. There can be infinitely many of them, but discrete. Also, we can have it on the boundary. Okay, and on the boundary, the only point of accumulation are some parabolic points. So here from outside, we can have plenty of post singular set, but these are the only accumulation points of the set in the boundary. And moreover, asymptotic values are generally outside the closure of U. So this is the situation. The next thing is some bound, quite weak bound on the degree of the map in this region. And the third condition is that U is tame at infinity, which means that here these unbounded parts are in some, say, P infinity. These are repelling petals at infinity, and here we have no critical maybe post-critical point we have, but not critical points, and so we have univalency, and dynamics is like that. Okay, so this is the situation. And
Sorry, question again. So in the second condition, the supremum is over here. W can be outside of U, right? So we're all images.
For Z in the closer.
But when you take supremum,
Yes, the parameter can be outside, yes.
okay.
Okay, so this is the result. Then the boundary is locally connected. In particular, we have generalization of the result for strongly geometrically finite maps for meromorphic case, but well, this is much more general. Okay. A corollary with some more work is the nice example of meromorphic transcendental Julia set, which is locally connected. This is exactly the Newton's method for sine. So we have here infinite number of attracting basins. This more or less vertical strips with decorations. Here there are poles, and this is magnification of the neighborhood of the pole. So this is part of the boundary of this attracting basins, and these are preimages. And we can prove that that all these components have locally connected boundary, and also the whole Julia set is locally connected. So to our knowledge, this is the first non-trivial example of a locally connected Julia set for meromorphic maps. Well, I say non-trivial because we have trivial examples. For instance, 2 times tangent Z is hyperbolic meromorphic maps, and Julia set is just real line. So it is local, but this is a bit of a trivial example. Okay, so this was an easy part of the talk. Now it's an easy part. This is the sketch of the proof. So one of the standard techniques to prove local connectivity is to construct some expanding metric near the Julia set. So this metric is a conformal metric, which is just which is a Riemannian metric of the given by some positive continuous function rho. This is the definition of the derivative with respect to this metric, and we say that this metric is locally contracting if or locally expanding if the derivative is strictly locally strictly smaller or equal or larger than 1, and uniformly contracting or expanding if the condition is uniform. Okay, so the standard method is to construct some good conformal metrics with some expanding properties. So what we really need is that near the Julia set or near the boundary of the Fatou component, we can estimate the derivative of backward branches by some term of converging series. And here it is written for the forward iterations of the forward, then it should be larger than 1 over the term of convergence series. Okay, this is not necessarily uniform expansion, but it is enough to prove local connectivity. I won't explain the details, but this is standard math used by many people listed here, also in transcendental set. So the usual candidates for this metric, when in classical hyperbolic case, it is just hyperbolic metric on some domain outside the post singular set. If we have critical points in the Julia set, we define so-called orbifold metric, which is a metric with some singularities at this point. And for geometrically finite maps, we also have to deal with parabolic points, and near parabolic point, we take another metric, for instance, Euclidean one, and we glue all this metric accordingly. This is the standard technique used in, for instance, in Milnor's books, in Carlson books. Okay, so what is our technique? So first we construct an orbifold metric on this, well, kind of compact part of the set, outside neighborhoods of parabolic points and outside neighborhoods of infinity. Then we defined a suitable metric, say petal metric, near the parabolic points and near infinity. Well, and then we glue them. And then we show this expansion problem. So it is not, so the technique is just I can say standard, but the new ingredient is this metric on this petal set infinity. Okay. Okay. So the first ingredient is this orbifold metric. So here we are interested in fact, in some set like this, we would like to have a good metric here, in fact, in some neighborhood of this green set. And this is a standard construction described, for instance, in Milnor's book. If we have a domain with a discrete set of post-critical points, one can define so-called orbifold metric. This is a Riemannian metric with singularities, but the singularities, we know exactly the asymptotic of this metric at this points. And what is important is that it is uniformly expanding on compact sets, this is a bit delicate. So we can have here post-critical points where the metric is infinite. But still, if we have, say, a neighborhood of this point, then we have uniform expansion here, outside of this point, because the metric is not defined. But the expansion is uniform. So this is a standard construction. The next ingredient are these parabolic points. Okay, we take this is a general situation. We take a parabolic fixed point with a multiplier 1. We defined attracting and repelling petal in the usual way, and then we take some good metric. So maybe I will also remark, because our notion of repelling petals is such that we would like to copy some properties of repelling petals for parabolic points. So what are the crucial properties of petals of parabolic points? So if you look at the behavior of the map in repelling, or here is attracting petal of parabolic point, so the distance between the point and its image is like well, the distance to the parabolic point in some power, yes, and the direction of this vector is almost the same as the direction towards the parabolic points. This is standard analysis of parabolic behavior near parabolic points. So remember this, and here we take a good metric. Here is generally a metric of this form, where alpha is something between 0 and 1. We can, for 0, it is Euclidean metric. Okay, and we just by usual analysis, like for Fatou coordinates, we have the following estimates. So for attracting petals, the derivative of nth iteration is smaller than some an. Here, this an is just explicit. One can write this. What is important for us is that well, the series is convergent, and we have this condition. So this an is a decreasing sequence, but the slow. But well, the ratio between two consecutive terms is becomes larger and larger. Yes, and well, it is you should think of it as, for instance, an is like 1 over n squared. This is a standard example. Okay, so this is the analysis for parabolic points, and now we would like to define something like this at near infinity. So we just try to impose some minimal conditions so that we can repeat the analysis. So our definition is like that: an attracting petal at infinity for a map G is something, well, it is mapped inside itself with the closure. Generally the points go to infinity, and these are analogs for these two conditions for parabolic points. So the distance between points and the image is like some function g of modulus of z, which we assume that it is decreasing and logarithmically convex. And also the direction of this vector is almost the same as the direction of the vector z. And I will explain it on the picture, okay? So we have a point z, it is far away near infinity, and here is the point g of z. So we assume that the distance between z of g of, and capital G of z is like this small g, this decreasing logarithmic convex function. And here, and the direction of this vector is more or less like the direction of vector z. It need not be very close. It just the condition is that this is smaller than 90. This delta is smaller than 90 degrees.
A question. So in the condition on G it says non-increasing. Does it mean that it can be, say, constant?
No, yes, it can be constant. Yeah, it can be constant. And in fact, these are the standard examples.
Okay.
So,
well, a repelling petal is something, we take an attracting petal and the inverse of the map, and we have repelling petal. So these are the standard examples for this logarithmic convex function g. But a basic example is the following: we have right half plane. The map is like z minus 1, and everything goes to the left. This is the standard example. Good. So in this repelling petal at infinity, we have another metric of this form, and the difference between this and parabolic was that for parabolic alpha was between 0 and 1, and here it is larger than. And we have an analogous estimate of the derivative. In attracting petals at infinity, the derivative of nth iteration is estimated by an, where an is like for this parabolic points. The only difference is that we cannot achieve 1 here, but some constant. Good. Maybe I will just comment, and then to prove this estimate, we use this beautiful theorem, which we call Cohen-Baker-Pomerenke theorem from the 80s, which is a kind of generalization of the Fatou coordinates. But I have no time to comment on this. Okay, and or maybe I have time. So maybe okay, so maybe I will say something. This is a general theorem, but here is for this petal, we have simply connected domain and a holomorphic map on this simply connected domain into itself. And the theorem says that we have a semi-conjugacy on the whole domain with the translation. And there are three cases. This translation is either on the strip, half strip, or the whole plane, and we call this cases hyperbolic, simply parabolic, and doubly parabolic. And moreover, this semi-conjugation is in fact actual conjugation on some domain V here, which is an absorbing domain. So every compact set after some time is mapped into this domain. Yes, so we use this to prove this estimate. Okay, and now we gather all these ingredients, So we take this orbifoltmetic on the suitable domain. Oh, maybe I write it here. So we take a set which is called here K tilde. This is a compact set with a boundary, but it is away from parabolic points. Okay, here I will draw a petals of parabolic points. Yes, so we see that the rest of the sets outside K tilde is in these petals. And now we take this orbifoltmetic on this compact part. Yes, here on this compact part, we take this petal matrix here, and in the middle we take minimum. Well, actually, this minimum, when we are close to infinity or close to parabolic points, it is achieved here. So it is the petal metric, and just in between we have this minimum, and then we have a good metric. And this is the final computation. So now we take a point which is here. We assume that we are here all the time, but we can jump. At some point, we can jump into the petal, and then we go here, here, here. We return to the compact part. We are here. Maybe we can jump here and return. Also, we can jump here and return. Okay, and if we know that if you are in this compact part, then we have uniform expansion. If we are in these petals, we have no uniform expansion, but we have an estimate of this kind, that the derivative is larger than 1 over some convergent term of convergent series with this mysterious condition. But this condition gives something like that. That the term with index p plus q is larger than the product. And now we divide the whole trajectory into blocks, like I explained, and we estimate the derivative by the chain rule. And the crucial thing is that we have here we have a product of this terms of this converging series, and we can estimate by one term with the index being the sum of indices, and then if we just count the total time we are in petals and in the compact part. If this time when we are in the compact part is at least a half of the total time, then we estimate the rest by 1, and we have convergent term like q to the power n half. And if we are in other case, we are at half of the time we are in petals, and we forget about this q, and we take this other term in the index n half, and we are also done. So this is a general construction. Thank you very much.
So, okay, this you mentioned this cone maker from a rank. So where exactly does this enter here?
It is And it's estimate of the derivative. Just advertise.
Yeah.
Because you need some, distortion estimate, and this gives you distortion estimate because you have conjugation with the translation. It's just for that.
Hakan, yours for the question?
Yes, I wonder if this metrically constructed can help say something about how to dimension of Julia's set, something like that.
I think yes, but rather some estimates from above, because we have just estimation from one side. So generally saying that yeah, there is expansion. So it gives.
Maybe directly on that, but even for this example, you had Newton method, the sine function. So the z minus 10 would be so. Would you get something on out of dimension, say out of dimension of Julia's set less than 2 or something?
This is our work in progress with my PhD student, Joanna. This is, yeah.
Any questions from online? Then let's thank this.